Okay, here we are. This is a lesson on the Born-Haber cycle. Okay, I'll be as quick as I can. Okay, right, and I'm recording this, so I'm going to put this up on YouTube later. Now, before we look at the Born-Haber cycle, we have to look at other enthalpy changes. Enthalpy changes. All right, now I think the first most important one is the enthalpy change of hello. Hi, Kathleen. How are you? I'm. I'm good. I've started the lesson. Okay. So here we are. Enthalpy changes. All right. Now there's a few we've got to know. We've got to know the enthalpy of hydration. Okay, that is one we have to know to talk about the Born-Haber cycle, and we're looking today at the Born-Haber cycle. So what's the enthalpy change here? This enthalpy change is, all right, it's when 1 mole of gaseous ions, I'm going to call them, let's do magnesium, 1 mole of gaseous ions goes to 1 mole of aqueous ions, and this would be the heat of hydration for the magnesium 2 plus ion. So let's look at what's going on with the heat of hydration. All right, what's going on is this. Imagine I have two group 2 atoms here. Okay, oopsie daisy. All right, let's have a look at this one. This is a group 2 ions. This is a magnesium ion, and this is a calcium ion. Okay, and I'm going to hydrate them both. This has a charge of +2, and this has a charge of +2. Now, a water molecule looks like this. Okay, it's delta minus, delta plus, delta plus. So we can approximate a water molecule by a V shape, where the pointy bit is delta minus, and these bits are delta plus. So that means if we hydrate a magnesium ion and we hydrate a calcium ion, you're going to get this. There's the magnesium ion, and there is the calcium ion. So this is 2 plus, and this is 2 plus. They're both 2 plus. And the water molecules will go around. They'll be attracted to the ions here, and you'll get these. These will be attracted like this, with the H's closer to the ion. It will also happen to the calcium ion. There you go. Okay, now when this happens, let me do one up the top there. When this happens, okay, and bonds are being formed. Okay, so bonds formed. All right, and so both of these are going to be exothermic because bonds are being formed. All right, now, so the enthalpy change is going to be negative. Okay, so this is going to be, so I don't know, minus 900 or so. Now this one is going to have a smaller heat of hydration. It's going to be, say, minus 700. Now the reason it's less is because the magnesium ion is smaller, and the magnesium ion therefore has a higher charge density. So the Mg2 plus has a higher charge density, and therefore the attraction for the water molecules will be greater. Attraction for water molecules is greater. Okay, that's why the enthalpy change here is more negative than the enthalpy change there. Now let's just finish this off. The calcium ion is bigger, and because it's bigger, it has a lower charge density. Okay, this idea of charge density, you really want to get into your heads. It's very important. All right, since it has a lower charge density, the attraction for the water molecules is less. attraction for H2O is less. Okay, so one thing we have to know about hydration energy is this. Okay, it's that process where the ions are getting hydrated, but the smaller the ion, the higher the hydration energy. There you go. So that's enthalpy of hydration. That's one thing we have to know, okay, in this thing. All right, another one we have to know is the enthalpy of solution. Enthalpy of solution. Now this is when 1 mole of ionic compounds, whoops, it's not that, 1 mole of solid ionic compound is dissolved to give us 1 mole of aqueous ions. Cl minus, oh that's ugly, isn't it? Cl minus aqueous. Okay, that is defined as the enthalpy of solution when we have 1 mole of this and we get the aqueous ions on this side. And this is defined as the enthalpy of solution. That one we got to know about, so please, if you don't know that one, look that one up. Another one is, I'm sure you know this one, but let's do it quickly. This is the ionization energy. Okay, and this is when 1 mole of gaseous ions, let's do sodium again, why not? When 1 mole of gaseous, sorry, not ions, when 1 mole of gaseous sodium atoms is converted to 1 mole of gaseous ions with a charge of plus, and this is regarded as the ionization energy, and this is called the first ionization energy. We got to know about that one. And the last one before we start doing it, let's have a look at one called electron affinity. You have to know about this ionization as well. So this ionization is, let me push this up. This is another ionization, but it's a negative one. Okay, this is when non-metals, gaseous non-metals, gain an electron to form negative ions. And this one is called electron affinity, EA. One last one, very quick last one. This one is bond energy. And the bond energy is this. It's how to break 1 mole of specified bonds, this thing, to give 2 moles of atoms. Now, if we break 1 mole of bonds there, 1 mole of bonds are breaking, it's known as the bond energy. Bond energy. Now, if we do exactly the same process, but we get half as much, I'll show you what I mean. It's a bit weird, this. All right, if we start off with Cl, Cl, and we end up with only 1 Cl this side, in other words, we start off with half these, this one is known as the atomization. Now, they look very similar, don't they? One's twice as big as the other. The bond energy is talking about breaking 1 mole of bonds, but the atomization is about forming 1 mole of atoms. So this is forming 1 mole of atoms. And look, these are a pain, trust me, but you've got to know all of these changes, all of these enthalpy changes. Now, let's go on and do, if we can, let's make that a bit smaller. Now I'm going to do the Born-Haber cycle for something like magnesium chloride. Here we go. So I'm going to start at the bottom, and I'm going to start off with magnesium chloride solid. That's the bottom rung, okay? Now I'm going to start off here, and I'm going to have magnesium solid plus CO2 gas. All right, and that is the first enthalpy change in my Born-Haber cycle. Anyone know what that one's called? What's this energy change? From this to this. Anyone? No one. All right, this is known as the enthalpy of formation of magnesium chloride because we're making it from its elements. Now we're going to go up to the next level, and the first thing I have to do is I have to vaporize my magnesium. So I go from solid magnesium to gaseous magnesium. This change is the delta H of vaporization of magnesium. And my magnesium's gone from a solid to a gas. I haven't done anything to my chlorine. All right, next, I'm still working on my magnesium. So next, I want it to be +1 charge, Mg plus gas. There's the electron I've taken off, plus Cl2 gas. So I haven't done anything to the chlorine. I've just done an ionization energy of the magnesium. This change is ionization energy of magnesium gas. Then I've got to ionize it again because I want Mg2 plus, because that's how it is, isn't it, in magnesium chloride. So I do another one, Mg2 plus gas. There's 2 electrons taken off now, and there's my chlorine. The magnesium is good. I'm done with my magnesium. Next thing I want to do is I want to break up the chlorine now into atoms. Okay, so there's another change here. All right, and what's this one? This one is Mg2 plus gas plus 2 electrons plus 2 chlorine atoms. Okay, so I've got the chlorine like that. Now I want to add an electron to my chlorine. And I add 2 electrons to 2 chlorine atoms here. So what do I get? I get Mg2 plus gas plus 2 Cl minus gas. These electrons have gone onto the chlorine. And last of all, as you can see, the last stage is that. And that is the enthalpy change of lattice formation of magnesium chloride. Okay, so let's have a quick look at that one, that lattice energy. Before we're going to have a look at that thing again. All right, the lattice energy is this. It is the formation, we'll talk about this in a minute, but the formation of 1 mole of solid ionic compound from its gaseous ions. So, for example, let's do magnesium chloride. Mg2 plus gas plus 2 chloride ions, gas, gives us MgCl2 solid. That is the lattice energy of magnesium chloride. Now, so this, ions are coming together, so bonds are being formed here. So in this case, the lattice energy, delta H lat, of this guy is going to be exothermic. I don't know how many. I'm going to pretend I know. 1200 kilojoules per mole. It's probably a bit more than that. All right, so that's the lattice energy of formation. This is the lattice energy of formation. And the lattice energy of formation will always, always, always be exothermic because ions are coming together to form the lattice. Now, let's have a look at the reverse reaction. Let's get a different color. If I smash up the lattice like this into Mg2 plus gas and 2 chloride ions gas. Now, obviously, it's exactly the same process, but it's in reverse. So this one is going to be delta H lattice, believe it or not again, but this time we're breaking it, so it's going to be plus 1200 kilojoules per mole, because we're breaking the lattice. So what on earth is going on? Well, this one would be called the lattice energy of dissociation. because we're breaking up the lattice. So you have to be careful. If you're dissociating it, you're breaking it up. If you're making it, you're putting it all together. If you're putting it together, it's exothermic. If you're breaking it apart, it's endothermic, which is really a big deal. All right. So there we go. We've got that. So let's go up to this thing. So this is a Born-Haber cycle. All right. Now, the good thing about this is all of these numbers added up together, because it's a cycle. Does anyone know what it all adds up together? This is a Born-Haber cycle. If you add all of these numbers up together, what must they equal? Anyone? No? I guess no. All right, all of it added up together because of Hess's law must equal 0. Yes? Because if you start at magnesium chloride and you go around the cycle and you end up at magnesium chloride, it's bound to be 0, isn't it? So what does 0 equal? I'm going to go up this way and down this way. So this is the route I am taking. And I'm going to add everything together. So I'm going to start from magnesium chloride. So it equals minus delta HF, the formation, plus delta H vaporization, plus the first ionization energy of magnesium, plus the second ionization energy of magnesium, plus the bond energy of chlorine, plus 2 times the electron affinity of chlorine, plus the lattice energy. All of that is equal to 0, and that's a Born-Haber cycle. Does that make any sense at all? Are we good with that? Okay, I'm going to get a question on this because it's a nice topic. Where are you? It's not AQ. Yeah, I want AQA. Whoops, lazy. AQA. Let's go to 2020. A2. All right. Let's have a quick question on it so you understand it. All right. So we're going to an AQA paper 20 something like that. 2020. All right. This is a lovely question on the Born-Haber cycle. So let's grab this. Okay, so this one is for strontium chloride. Very similar to the one we've just done. Oops, let's move this up. Okay, there it is. Let's grab this. This Microsoft is a real pain. Right, there we are. There is a Born-Haber cycle for strontium chlorides. Okay, nice one there. All right, figure shows enthalpy changes. There's Born-Haber cycle for strontium chloride, and there you go. All right then. So let me look at their one and see if I can. Where are we now? See if I can. Whoops! I'm sorry, guys. I'm trying to find the. There it is. See if I can tell you about the energy changes here. All right, it's exactly the same. They're all the same. That's why they're easy questions. This one is enthalpy of formation. This one is we're vaporizing the strontium. This one is we are atomizing the chlorine, or the bond energy of chlorine. This one is the first ionization energy of strontium. This one is the second ionization energy of strontium to give us Sr2+. And this is the electron affinity of chlorine, and this is the lattice energy. Does that make sense in principle? Now, we're not going to manage to do all of it in a quick half-an-hour lesson, but do you get that? Well done. It's not hard, this. It really isn't. It's easy to get marks on this. All right, so let's go back to the question, and let's get the data. This is what they call the thermodynamic data. All right, here it is. Okay, let's stick that in. All right, let's move this up. There it is. And as always with Microsoft, it pastes it in a weird way. All right, so let's make that a bit smaller. Let's get everything in. Let's move that down. And there you go. So that's all of the information that they give us in this question. And what they want you to do is calculate the electron affinity. Okay, there you go. There's the question. And there is the question they want. Look at that. It always does that. Paste it in a really weird way. Right, so there is the question they want us to do. They want us to find the electron affinity of chlorine. So let me drag this down. There. Make it a bit bigger. All right. So, do you want to do it or shall I do it? Guys. Anyone can do what you want. But do you want to do it or shall I do it? Thumbs up for you'll do it. Thumbs down, I'll do it. Oh, good. Well done, Emmanuel. All right, then. I'll leave you for 5 minutes. All right. Do your best and I'll come back. All right. I'm literally going to go and get a cup of tea. And my back is killing me, so I have to stand up. So I'll see you very shortly. I'll be back in 5 minutes. Testing. Hello, anyone done? Are we good? Shall I do it yet? I guess you're still working on it.
Yeah, we're still working.
Okay, no problem. Go for it. You can talk to each other, by the way, if you want sort of some collaboration. How about now, guys? You've done it. All right. What answer you get? Any particular answer, or just a random one? Unfortunately, it is not. Okay, let me do it for you here. Okay, let me watch how I do it. Eh? Watch how I process it. All right, now I'm going to write my own Born-Haber cycle here. So watch this. I'm going to go all the way around like I did in the example and come back to here. So I'm going to say 0 equals, because the whole thing equals 0. That's very important. So I'm going to go here, from here to here. Oops, let me do that again. From here to here is going against the arrow, isn't it? So I'm going to call that minus delta H of formation. Now this is plus the arrow, and I'm going to call that plus the vaporization energy of the strontium. Then I'm going to go up here, and that is, what have I done there? That is the bond energy, isn't it? Bond energy of delta H, bond energy of the chlorine. Then I'm going to go up here, one more step. This is the first ionization energy of strontium. Then this is the second ionization of strontium, plus 2, sorry, what am I talking about? Plus 2, sorry, ionization energy seconds. This is ionization energy first. Then this is plus 2 electron affinities, because I'm doing it twice. And then the last one plus the lattice energy. Now, all of that rubbish there, what do I want? Of all of that stuff, all I want is this. That's what the question asked for, the electron affinity. So I'm going to put all the other stuff over the other side, and I'm going to say 2 electron affinities is equal to minus delta HF. Oh no, it's going to be plus, isn't it? Because I'm putting everything over the other side of the equation. Minus delta H vaporization minus the bond energy minus the ionization energy, the first one, minus the ionization energy of the second one, minus the lattice energy. All of that should give me 2 of those. So let's put the numbers in. Formation, I'm going to look at this now. Second enthalpy, this one. There's the first one. So this is plus this number, minus 828. Minus the vaporization. Where is that? Atomization of strontium, that one. Minus 164. Minus the bond energy of chlorine. Where is that? Oh, they call it the atomization energy of chlorine, which is fine, but therefore it is 2 of those, isn't it? It's 2 atomizations because we form 2 moles of atoms. So that's 121 minus the ionization energy of strontium, which is 548, minus the second ionization, which is 1060. All right, we've done that. We've dealt with that. And then it says minus the lattice energy. So it is minus 2112. Okay, so I'm going to work that out on my calculator as quickly as I can. All right, this is only a 3-mark question, so they're not regarded as that hard, these things. So it's minus 828 minus 164 minus 242 minus 548 minus 1060 minus 2112, and I get 730 so far. So I get 2 ionization, electron affinities is minus 730. Therefore, one electron affinity must be this divided by 2, which is 365 kilojoules per mole. And that is the answer. Let me grab the answer here. Let me see if I can done it. Nope, I have not. Let me get rid of that. Move that down. Grab this. No, grab that. Let me show you what I mean. And believe it or not, and it's hard to believe, but I didn't look at the answers. I just do it nice and gently and slowly, and make sure I know what I'm doing. And there you go. That's the answers. These are the official answers. Let me make that. Oops, make that bigger. There. Can you see? We're good. And that's what you do. Make this a bit bigger. All right. Again, make this a bit smaller. This is Microsoft is a real pain. Push that up there and make it bigger. There you go, that'll do. So, do you get that? Now, as I say a million times. Okay, where are we? Oopsie daisy. Sorry, I'm messing around with things this side. So, do you get that in principle? Now, you're not going to get these entirely, but you've got to just practice them. So that's how you do a Born-Haber calculation. Everything equals 0. You've got to practice them though. There's no way you'll get good at these without practice. Does that make sense? Are you good, guys? They're not easy, are they? They're not. Life isn't easy. Chemistry IB isn't easy. But there you go. So let me finish this video. I have technical issues with posting these things, but let me try my best. All right. Anyway, guys, have a great day, and I'll see you on Wednesday. All right. Take care. Bye-bye.